memory retrieval and entering
Have you ever actually thought about um, the physical weight of the internet?
the physical weight, like the servers.
Well, not the cables or the servers, but like the actual weight of
setting up the Ulefone Armor. This is the brief on setting up the Ulefone Armor 22 as a mesh node. We're basically taking a rugged, military-grade smartphone packed with a massive 10,100 milliamp hour battery and turning it into your very own piece of sovereign infrastructure using the Apex Armor Controller APK, completely bypassing traditional app stores. First, let's look at the installation process. To keep absolute control, you're going to dodge the Google Play Store entirely. Just download the APK straight from the Apex GitHub releases, transfer it over via USB, and tap it in your file manager to install. Think of it like sideloading a super secure, highly specialized tool directly into your pocket. Second, you need to grant some core permissions. Opening the app triggers requests for Wi-Fi, location, Bluetooth, and the phone's native IR blaster. Now, you might be thinking, wait, why does a privacy app need my location and an infrared beam? Well, the IR blaster is specifically for real-time 3D room mapping, while Wi-Fi and location handle mesh discovery and GPS triangulation. Rest assured, there is absolutely zero telemetry, no data collection, and it doesn't even require root access. Finally, we have the first launch sequence. It's a quick, 4-step setup. Grant those initial permissions, initialize the decentralized mesh, calibrate the IR beam, and configure your network. Once that's done, your device is actively scanning for threats, acting as a node that runs for 2 to 3 days straight on a single charge. So, with just a quick file transfer and a few calibration steps, the Armor 22 is totally ready for field operations.
Ready up, squad!
You've successfully built your own safe network, ready to route with mathematics, and own your infrastructure. This is the brief on setting up the Ulefone Armor 22 as a mesh node. We're basically taking a rugged, military-grade smartphone packed with a massive 10,100 mAh battery and turning it into your very own piece of sovereign infrastructure using the Apex Armor Controller APK, completely bypassing traditional app stores. First, let's look at the installation process. To keep absolute control, you're going to dodge the Google Play Store entirely. Just download the APK straight from the Apex GitHub releases, transfer it over via USB, and tap it in your file manager to install. Think of it like sideloading a super secure, highly specialized tool directly into your pocket. Second, you need to grant some core permissions. Opening the app triggers requests for Wi-Fi, location, Bluetooth, and the phone's native IR blaster. Now, you might be thinking, wait, why does a privacy app need my location and an infrared beam? Well, the IR blaster is specifically for real-time 3D rooming, while Wi-Fi and location handle mesh discovery and GPS triangulation. Rest assured, there is absolutely zero telemetry, no data collection, and it doesn't even require root access. Finally, we have the first launch sequence. It's a quick, 4-step setup. Grant those initial permissions, initialize the decentralized mesh, calibrate the IR beam, and configure your network. Once that's done, your device is actively scanning for threats, acting as a node that runs for 2 to 3 days straight on a single charge. So, with just a quick file transfer and a few calibration steps, the Armor 22 is totally ready for field operations. You've successfully built your own safe network, ready to route with mathematics, and own your infrastructure.
Imagine you were deep underground.
Right.
Your GPS is totally jammed, the external internet has been completely severed, and all you are holding is a rugged smartphone.
Just the phone.
Right. By all conventional logic, you are, digitally blind.
Absolutely. You'd be an isolated node with zero connection to the outside world.
Exactly. But according to the massive stack of patents and these wild architectural diagrams you sent us for today's deep dive, that phone still knows exactly where you are.
Yep.
It knows what precise microsecond it is, and it somehow knows how to securely route heavy data payloads across this sprawling global mesh network.
It's pretty incredible, honestly.
It really is. I mean, you brought us a fascinating set of sources today, diving into something called the Apex Domain Protocol.
Or Apex WRT.
Right, Apex WRT. And frankly, unpacking the materials you flagged, it's just tearing up everything we thought we knew about how the internet's supposed to work.
It really forces a paradigm shift. I mean, we've spent the last 30 years basically relying on the Border Gateway Protocol, or BGP.
The backbone of the internet.
Exactly. But fundamentally, BGP is just routers constantly asking their neighbors for directions.
Like, hey, where do I send this?
Right, and then storing those answers in these ever-expanding digital phone books. It's a system built entirely on lookup tables.
Huge tables.
Massive ones. But what the Apex documentation proposes is completely abandoning those traditional routing tables.
Just throwing them out.
Throwing them out entirely in favor of pure deterministic geometry and, well, localized physics.
Okay, let's unpack this. Before we get into the really heavy mathematics of replacing the routing table, I want to anchor us in the physical reality of the hardware.
Good idea.
Because the documentation you highlighted, it specifically details an APK called the Apex Armor Controller, and it's built to deploy on the Ulefone Armor 22.
Yeah, and looking at the specs in these sources, this is definitely not your standard consumer device.
No, not at all. It's a military-grade tank of a phone.
Yeah.
I mean, it's got IP68 waterproofing, Gorilla Glass, and this massive 10,100 milliamp hour battery.
It's huge.
But the main feature here, like the thing that actually makes this protocol possible in physical space, is the native...
Ready up, squad.
...940-nanometer infrared blaster built directly into the chassis.
And that IR blaster, it changes the fundamental nature of the device.
How so?
Well, the Apex app isn't just treating the Ulefone as a communication tool. It transforms it into an active spatial mesh network node.
Okay.
It uses that built-in IR emitter, which, by the way, has an effective range of about 20 meters indoors and 50 meters outdoors.
Oh, wow, it's pretty smart.
Yeah, and it continuously bounces these 38 kilohertz signals off the surrounding environment.
So it's actively scanning.
Exactly. It pairs those infrared reflection times with the device's internal telemetry to generate real-time 3D topographical maps of the room.
Just via continuous triangulation.
Yep, it maps everything locally.
So rather than just sitting there blindly broadcasting a Wi-Fi signal like a normal router, it's operating more like an echolocating bat.
That is a perfect analogy, yeah.
It's physically mapping its boundaries and constantly pinging the environment. And the documentation even notes it functions as an active threat detector, right?
It does. It monitors the local airwaves constantly.
And if the protocol identifies an unauthorized device or like a rogue access point attempting to piggyback, the Ulefone literally shoots out targeted death frames.
Just forcefully disconnecting them from the mesh.
That's wild. But that raises a massive mechanical question for me.
Okay, what's that?
A phone that is simultaneously running Wi-Fi 6 mesh networking, generating a 3D IR map of a room, and actively attacking rogue devices.
Right.
That sounds incredibly resource-intensive. And that doesn't seem like enough juice to survive a multi-day off-grid deployment, even with a 10,000 milliamp hour battery.
Well, it wouldn't be if the device were processing all those tasks using traditional linear software architecture.
Okay.
But the performance optimization statistics in the source material reveal a totally different operational footprint.
Really?
Yeah. The idle power draw of the Apex app is just 5 milliwatts.
Wait, 5 milliwatts?
Just 5. And under a full active mesh networking load, including all that spatial mapping, it only draws 200 milliwatts.
Wait, 200 milliwatts. That defies the physics of standard mobile processing. Standard location tracking alone usually pulls more than that.
It does. It absolutely does. But standard location tracking and network routing require continuous processor engagement.
Right, the chip is always working.
Exactly. The reason the Apex node can run the full active mesh for 50 hours straight on a single charge is because the routing mechanism itself is incredibly lightweight.
Oh, I see.
The processor spends the vast majority of its time in a deep microsleep between calculations.
Fascinating.
And this perfectly sets up the core breakthrough of the protocol. If you want to route massive amounts of data efficiently on constrained, battery-powered devices out in the woods, you absolutely cannot use traditional internet routing tables.
Because they're too heavy.
Way too heavy. BGP requires memory that grows linearly as the network expands. The larger the network, the more memory you need.
And modern machine learning algorithms.
They're just non-deterministic black boxes. They require massive computing power just to infer a pathway.
So Apex just sidesteps both.
Completely.
Ah.
By using an entirely new mathematical engine.
Here's where it gets really interesting. You directed us to the architectural wallpaper diagrams detailing the core of this system.
The TTPE, yes.
Right, they call it the Triangle Thought Process Engine, and it operates on something called an exponential squared table.
The EST.
Yeah, so BGP, as you mentioned, requires ON memory, but the PTPE requires O1 memory and O1 time.
Right, constant time.
Meaning the computational load is a flat constant. It requires the exact same microscopic amount of memory and time, whether it is routing a packet between 3 phones in a basement or 3 million phones across a continent.
And that constant efficiency is achieved by basically restructuring how data moves through a processor.
Okay, walk us through that.
The diagram illustrates what the creators call the 12 apostles.
Right, I saw that.
It's a matrix of 12 processing nodes split into 3 groups of 4. Group A, Group B, and Group C.
A1 through A4 and so on.
Exactly. Now, when a data packet needs to find its destination, it doesn't query a database. The network variables flow downward through 7 distinct mathematical layers.
Using a specific pipeline.
Yes. It utilizes a highly specific computation pipeline, a horizontal multiply, a vertical multiply, and finally an addition down.
So instead of a routing table asking who is the next hop and searching through a massive list, the TTPE is literally a geometric matrix.
You're just dropping numbers into a formula.
The input conditions like distance, gauge state, traffic density are mathematically forced through those 12 nodes, collapsing down through the multipliers until the final output vector physically points to the single correct spatial route.
It's routing via physics formula rather than a digital phone book.
It's amazing. And looking closely at the mathematics and the patents, there is an explicit reference to Nikola Tesla's 369 digital root theory.
Yes, that's a huge part of it.
The engine heavily utilizes logarithms and modulo arithmetic to partition the state space.
What's fascinating here is that the integration of base 3 logarithms is just crucial. A standard binary system is rigid.
Because it's just ones and zeros.
Right. It forces a yes or no evaluation at every node. By shifting the foundational logic to base 3, the engine inherently supports a yes, no, or maybe architecture.
A maybe state.
Exactly. That maybe state allows the routing engine to organically absorb dynamic variables, things like sudden network congestion or kinetic movement, without having to recalculate the entire routing table.
Oh, wow.
It naturally accommodates friction.
And because it relies on those strict modular arithmetic parameters, the routing is entirely deterministic and reversible.
Yes.
Like, modern ML routing might find a fast pathway, but if you feed a neural network the exact same input twice, microscopic variations in the weights might yield a slightly different route.
You can never fully reverse engineer why it made that specific choice.
Right. But with the TTPE, an exact input will always, unconditionally, yield the exact same output.
Which fundamentally solves one of the biggest nightmares in network security, which is auditing.
Because you can trace it back.
Exactly.
Yeah.
If you capture an Apex output decision, you can run the mathematics backward through the 12 apostles matrix to perfectly reconstruct the exact environmental input state that generated it.
That's incredible.
You have a mathematically flawless audit trail of every single routing decision.
Okay, so if the TTPE is the engine performing the calculations, the documentation details the superposition 10 factorial, or the S10 factorial, as the actual spatial roadmap the data is navigating.
The S10 factorial, yes.
The mathematics take a 7-variable input space and map it to exactly 10 factorial possible outcomes, which, doing the math, gives us 3,628,800 discrete routing permutations.
3.6 million realities, essentially. And rather than calculating those permutations on the fly, the system utilizes a lemma code injection.
A lemma code projection, right?
For the listener reviewing these charts, a lemma code functionally acts as a translation layer. It assigns a unique sequential integer to every single possible permutation of a set.
Okay, so it just indexes them.
Exactly. By utilizing this projection, the Ulefone precomputes all 3.6 million of those routing realities at startup.
Wait, all of them?
All of them. The entire matrix is generated in just 5 to 10 seconds when the device is powered on.
But wait, this introduces a massive practical bottleneck, doesn't it?
How so?
If the protocol is evaluating over 3.5 million permutations every single time it wants to push a packet across the mesh, wouldn't that introduce debilitating latency?
Ah, I see what you mean.
I mean, if I'm using this off-grid mesh in a highly volatile scenario, evaluating millions of realities sounds like my connection is going to be incredibly slow.
That assumption totally makes sense if we think about evaluating data linearly, like, searching a massive spreadsheet.
Right.
But remember, the lemma code projection means finding a route is just calculating a single integer index. It's not searching a list at all.
Oh, because of the O1 memory?
Yes,
Right.
because the TTTE memory and time lookup is that flat constant O1, selecting the absolute optimal route out of those 3.6 million pre-computed realities, takes the processor less than 1 millisecond.
Less than a millisecond to parse 3 million spatial options.
That's exactly. The source documentation shows the total system latency for a packet is between 15 and 60 milliseconds.
Oh, wow. So it's basically instant.
Right. That means the transmission delay is completely dominated by network physics. Literally just the actual time it takes radio waves to travel through the atmosphere and process hardware interrupts.
So the routing logic itself evaluates millions of realities almost instantaneously.
Exactly.
Okay, so we have these rugged nodes evaluating millions of routes in a millisecond using base 3 geometry. But to execute these microsecond routing decisions across multiple independent, physically separated devices, the entire network has to be flawlessly synchronized.
Perfect timing is required.
Right, if node A and node B are even a few milliseconds out of phase, the data packet drops into the void. So how do you synchronize devices that are totally cut off from the external world?
It's a huge challenge.
They don't have internet access to ping a time server, and if they're deep underground or actively jammed, they don't have GPS.
You flag patent B for a reason because this is where the physics completely replaces the software.
Okay.
Patent B outlines the phase envelope, or what the creators call sovereign time.
Sovereign time.
Yeah. In traditional architecture, devices use Network Time Protocol, or NTP. They reach out to an external server to ask, hey, what time is it?
And Apex doesn't do that.
The Apex protocol abandons external time entirely. It derives sovereign time purely from local physics, using 3 self-referential calibration methods.
I love the mechanics of this. It's like a group of people trying to synchronize their watches deep inside a pitch-black cave.
Right, no sunlight.
No sunlight, no external clocks. So instead, they measure the specific rotational inertia of the rock beneath them. They measure the Earth's magnetic pulse. And they throw tennis balls to each other in the dark, measuring the precise distance based on how long it takes to catch the ball.
Completely ignoring whatever the atomic clock on the wall outside the cave says.
Exactly.
That analogy actually maps perfectly to the mechanical reality of the 3 calibration methods outlined in the patent.
Let's hear them.
Method 1 is gyroscopic integration. The phone's internal inertial sensors continuously measure angular velocity over time.
Okay, so movement.
Method 2 relies on the device's magnetometer, literally measuring the Earth's magnetic field, which correlates with the physical rotation of the planet.
Wow.
And method 3 is signal reflection calibration, your tennis balls.
Ah, bouncing the signals?
The mesh nodes continuously bounce probe signals off one another. Because the speed of light and radio frequencies are constant, they can measure the exact round-trip time.
So they know exactly how far apart they are.
Right. If a node's internal clock begins to drift by even a fraction of a millisecond, the signal bounce time detects the anomaly and corrects the drift within exactly 33 seconds.
But why engineer something this complex just to avoid pinging an NTP server? Like, what is the actual functional advantage of sovereign time?
If we connect this to the bigger picture, it's about complete and utter immunity to temporal spoofing.
Spoofing time.
Exactly. If a military network or an emergency disaster mesh relies on an external NTP server or a GPS satellite to dictate its time, it has a glaring vulnerability.
Because someone could fake it.
Right. An adversary with the right equipment can jam the GPS signal or, worse, spoof the NTP server to feed the network fake timestamps.
And if the time is wrong,
If you feed a decentralized mesh network contradictory time data, the routing collisions will cause the entire infrastructure to collapse on itself.
oh, it just breaks.
Yes, by deriving time strictly from localized angular momentum, terrestrial magnetism, and internal signal bouncing, the Apex network is physically quarantined from external manipulation.
Because you cannot spoof the physical rotation of the Earth.
Exactly.
That is wild. So you've got off-grid phones bouncing signals to keep perfect time, and base 3 math finding the fastest route in a millisecond.
Yep.
But if this network is completely decentralized and operates entirely on local physics, what stops an adversary from just walking into the woods, turning on an Apex phone, and injecting malicious code into the mesh?
That's the final piece of the puzzle.
How do you verify the identity of the data and the firmware itself traveling across this network?
This brings the entire system together in Patent C. The Sovereign coin, or S10 coin, and its integration with the Apex WRT firmware.
Okay, the S10 coin.
In standard network environments, to verify that a firmware package hasn't been tampered with or that a user is authorized, the system checks a static SHA-256 hash.
A fixed string of numbers.
Right, it's a fixed dead checksum. ATEX entirely replaces that static check with a dynamic, multidimensional 256 hash coin.
And the documentation you provided breaks down exactly what multidimensional means in this context.
It's quite literal.
Yeah, the hash isn't just a random string of numbers. It's constructed from 6 distinct physical and digital dimensions.
6 layers of verification.
Right. It requires a spatial dimension, verifying the exact physical location of the node within the mesh. It requires an identity dimension, validating the specific cryptographic keys of the owner.
Yes.
It demands a temporal dimension, locking the coin to a specific sovereign time window. But it also incorporates a kinetic dimension based on that localized gyroscopic drift we talked about.
And the hardware fingerprint.
Exactly, pulling from the Ulefone specific silicon variances, and a topological dimension that checks the current shape of the entire local mesh. All 6 dimensions must align simultaneously to validate the coin.
And we can see this multidimensional validation operating in the real world right now.
We can.
Yeah, you pointed us toward the DNS-TXT records included in the source files.
Still right.
There is a literal list of 19 active root domains. Brands like apex-airsolutions.com, caresolutions.tech, apexersolutions.net.
Saw those.
If you query the root of those domains on Cloudflare or GoDaddy today, you will find these massive 64-character hexadecimal strings labeled CoinVerify.
Sitting right there on the public internet.
Those TXT records are actively proving sovereign ownership of those domains by cryptographically binding the physical Apex mesh nodes directly to the web domain in real time.
Which perfectly explains the visual assets generated for this system. Looking at the provenance documents, the creators designed these highly complex green and red holographic OLED coin QR codes.
Right, the visuals.
The green interface is designated for users, the red for administrators. But they aren't just standard square QR codes.
No, they're much more intricate.
They have these neon glowing 12-point compass roses built into the center, layered with depth of field effects. Initially, I thought it was just an aesthetic choice, but looking at the mechanics, it's actually a literal schematic of the cryptography.
The visual design is a direct manifestation of the mathematics. The 12 points on that compass rose physically represent the 12 apostles.
The processing nodes.
Yes, mapping the TTPE engine we discussed earlier. Furthermore, if you analyze the optical density of those holographic QR codes, they utilize a strict 7-layer visual structure.
Oh, wow.
That depth directly mirrors the 7-layer scoring calculations of the TriStar routing engine. The graphic design is functionally visualizing the multidimensionality of the network state.
And the computational complexity analysis provided in the sources illustrates just how impenetrable that multidimensionality is.
It's staggering.
If a bad actor wanted to brute force a single one of these S10 coins, assuming they possessed a server farm capable of processing 1 billion operations a second, the math indicates it would take 10 to the 69th power years to crack.
To put that mathematical scale into perspective, the estimated age of the observable universe is roughly 10 to the 10th power years.
That's absurd.
Cracking this cryptographic envelope vastly, incomprehensibly outlasts the lifespan of the universe. It is functionally uncrackable by modern or theoretical brute force computing. And more importantly, because the coin requires those temporal, spatial, and kinetic validations, replay attacks are structurally impossible.
Because the moment passes.
Exactly. Even if an adversary intercepted a perfectly valid S10 coin and tried to inject it into the mesh 5 seconds later, the coin would instantly fail.
Right.
The temporal window would have shifted, the localized kinetic drift of the hardware would have changed, and the spatial topology of the mesh would have evolved. The coin dies the millisecond it is used.
So what does this all mean for you, the listener, who brought us down this incredible rabbit hole?
It's a lot to process.
It is. Even if you aren't prepping a military-grade off-grid mesh network today, the stack of patents you sent us clearly demonstrates the fundamental fragility of the internet infrastructure we rely on every single day.
Oh, absolutely.
Right now, global communication is chained to massive, bloated lookup tables that just gorge on memory. We trust our digital security to static checksums that can be stolen and replayed.
And we synchronize our entire global economy using external time servers that can be effortlessly jammed or spoofed by anyone with a transmitter.
But the Apex protocol proves that we do not have to build networks this way. It proves there is a tangible, deployable way to route massive data payloads using pure geometric mathematics.
To derive absolute time from localized physics.
Yes, and to truly own your infrastructure without ever asking an external server for permission.
It really demands that we completely rethink our foundational assumptions about what security actually is.
How so?
Well, the current digital ecosystem is obsessed with static passwords and stored keys. We type a string of characters into a prompt, or we save an encrypted file to a server and we assume we're secure.
Right, a password is just a secret you know.
But what if the ultimate uncrackable password isn't something you type or something you remember?
Okay.
What if the only true password is exactly where you are in physical space, the specific electromagnetic footprint of your hardware, and the precise rotational physics of the Earth, converging at the exact microsecond you connect?
A password constructed from the immediate physics of reality itself. From a rugged smartphone mapping a room with infrared light to routing data based on the magnetic spin of the planet.
Exact.
Thank you so much for bringing this incredible stack of sources to our attention and for joining us on this deep dive. Keep questioning the infrastructure you interact with every single day. We'll catch you on the next one.